Okay, so we're going to continue talking about polynomials, and now we're going to talk about polynomial division. Now, honestly, this is something you're probably not going to do a lot of in future math classes, but it is an important skill to have. And so, the nice thing I like about polynomial division, to me, is that it very much behaves like what we're thinking of with long division. Now there's also a method called synthetic division. Some people really like that method. I'm not a huge fan of synthetic division. Some people say there's some really good, powerful, and yeah, it's okay. But I'm more of a fan of just doing the straight out long division. And so before we do that, we want to first say here that let's go ahead and kind of talk about something called the division algorithm. And so we're going to have f at x and d at x are polynomials such that d at x does not equal 0. And the degree of d at x is less than or equal to the degree of f. Okay, so suppose we have this, then there exists unique, and of course what we mean by unique is that there's only one set of them, polynomials q at x and r at x such that f at x is equal to d at x times q at x plus r at x. And here we think of q at x, you can think of this as the quotient. Maybe I try to spell quotient properly. Quotient, and r at x you can think of as the remainder. Now there's some other things we know about r at x. For instance, we know that the degree has to be less than or equal to f, degree of f, but I'm not going to write that here. One important thing to note here if r at x equals 0, then d at x is a factor of f at x. Okay, so let's go ahead and see how we would write this if we were doing a problem. Sometimes you would write this as f at x divided by d at x, and this is going to equal q at x plus r at x over d at x. And really, this on how we do it in a problem, this is no different than the equation we have up here. It's just we divided everything by d at x. Alright, so how do we do these? Let's just do a couple examples of this long division here. The one thing you want to keep in mind here is where you want to write down f at x and include any missing terms by adding zeros in. And we'll talk about that in a second here. Then we're going to do the same for d at x. And then we're going to look always at the lead terms. And then I'm going to say do long division. Because I'm not really going to go into some texts like to go into a whole elaborate thing on, well, you divide these things first and that's what you would do, and then you have to do. I just say do long division. Okay, so let's just go right now with an example here. If my thing will zoom, there we go. Alright, so let's look at this example. So we're going to do x cubed minus 2x squared minus 9 divided by x minus 3. Okay, well, first off, this here is my f at x, and this is my d at x. So let's write my f at x down, including zeros for any missing terms. And we can see this in here in a second as we do this. We have x cubed. The next thing down would be x squared, and I do have that, minus 2x squared. And then I'd have an x, but I don't have any x's. That's not, that would be the next thing down from x squared, but there are no x's. So this is where you have to put in that placeholder 0 plus, and I like to write just 0 times x to indicate that's what I'm using it as a placeholder as. And then of course after x is just constants, and so I'd have minus 9. Now the reason we need to do that is because we might have x's showing up in the process, and so we want to make sure we have the placeholders there. And then I'm going to divide this by the term x minus 3. Now there's no placeholders or any additional things that I need to have there in order to keep that there. Okay, so then let's go ahead and take a look at this. Now what we do, as I said, we look at the first terms here. So I have x and x cubed. And this is where some books will say, okay, take the ratio of x cubed and x, which you can do. I'll put that off to the side here. If you do x cubed over x, what do you get? You get x squared. Now, I like to think of it a different way. This is an okay way of thinking it. I like to think of it, what do I multiply x by to get x cubed? Well, what would I multiply? I'd of course multiply by x squared. So I'd multiply x by x squared in order to get x cubed. So then, now that we've done that, we're going to do x squared times everything here and line things up. So what do I mean? X squared times x is x cubed. X squared times negative 3 would be minus 3x squared. So we're going to line that up. Now, when we did normal long division, what did we do? We subtracted. Okay, so we're going to do the same thing here. We're going to subtract. And some people like to then convert those to pluses. It's fine if you want to do that. I just like to think of it as x cubed minus x cubed. Well, that would be 0x cubed, right? So if it's 0x cubed, we just wouldn't bother writing it down. And then you have negative 2 minus negative 3. So that would actually be negative 2 plus 3, which is plus 1. So I'd have a positive x squared. Now, just like we did with long division, we bring the next term down. The next term is 0x. And now, let me just go ahead and erase this x cubed here, because that's not part of the answer. I'm hitting the wrong button. Alright, so I have a positive x squared plus 0x now. Now, this is where the long division comes in. I'm going to just keep doing the same thing. So now I'm going to look at x and x squared. What do I multiply x by to get x squared? Well, of course, we should see pretty quickly. What do? You multiply this by x. So I'd have, and now the key thing is that since it's x, it's going to be plus. Now, when would it be negative? Well, if I had to multiply by negative x, for instance. And again, another way you can do that is if you do the side thing and look at those two lead terms and do the ratio. X squared over x is simply just x. All right, now we're going to do the same thing here. We're going to distribute. So x times x is x squared. X times negative 3 would be minus 3x. And then, what do we have here? Well, we need to subtract then. So I'll put those in parentheses and subtract. And let's go ahead and switch up another color here. So x squared minus x squared, again that's 0. These terms should always start canceling out for us. Then I have 0 minus negative 3. So that would be positive 3. So I'll emphasize positive 3x. Then bring down the next term, which is minus 9. Okay, now we have one more to do. I have to ask myself, what do I multiply x by to get 3x? Well, of course, we'd multiply that by a positive 3. And again, if you want to think of it, you could think of it as the ratio of those lead terms, 3x over x, which is 3. All right, and so then, again, we're going to do the distribution. 3 times x is 3x. 3 times negative 3 is negative 9. Then we subtract. Now, it turns out that when we subtract, we end up getting 0. So my remainder is 0. Now, let's write our answer, dear. So what do we have here? Well, x cubed minus 2x squared minus 9 divided by x minus 3 is equal to x squared plus x plus 3. Now, this is actually a pretty big deal because I got a remainder of 0. Now, we'll look at an example where we don't get a remainder of 0 here in a second. But because I got a remainder of 0, what that means is that I could write x cubed minus 2x squared minus 9 is equal to x minus 3 times x squared plus x plus 3. And what's the big advantage of this now? Well, imagining that we were trying to factor. Since we found out that x minus 3 is a factor here, I factored it down, and now I have x squared plus x plus 3, which I could apply the quadratic formula to. So the key thing here is that with these long divisions, sometimes things that aren't factorable, as long as we know a couple of the zeros, we'll get 0 remainder, because if it's 0 remainder, that's the special case where we become a factor, or a 0, and then we could actually factor these completely. Now, we're not always going to get 0 remainders, so let's look at another example. Let's look at negative x cubed plus 9x plus 6x to the 4th minus x squared minus 3, and we're going to divide this by 3x plus 1. Alright, so let's first again write down the term that I'm dividing. Now, this one was kind of purposely written out of order a little bit. You do want to write these in descending order. So the 6x to the 4th, of course, is the biggest one here. So we would have this as 6x to the 4th minus x cubed minus x squared plus 9x minus 3. I don't know why I put those parentheses there. And this is all divided by 3x plus 1. Now, same game here as we've done before. So we're just going to ask ourselves, what do I multiply 3x by to get 6x to the fourth? And again, if you can't think of it, you could do 6x to the fourth divided by 3x, and that would get you 2x cubed. But I think it's pretty straightforward just to kind of think about it in your head. What would I multiply 3x by to get 6x to the fourth? Well, you multiply by 3 by 2 to get 6. You'd multiply x by x cubed to get x to the fourth. So we would have then 2x cubed, and then we'll go ahead and do all the multiplication out here. So we'd have 6x to the fourth plus 2x cubed, and then we do the subtraction. So then when I subtract, the 6x minus 6x is 0. Then I have negative 1 minus 2, so this would be negative 3x cubed, and I bring down the next term, which is minus x squared. Now, what do I multiply 3x by in order to get negative 3x cubed? Well, that would be minus x squared. So then I do, again, kind of the same thing, distribute minus x squared times 3x. So I'd get minus 3x cubed, and then I'd have minus x squared. Turns out this is still not going to have a remainder here. We'll look at one that will have a remainder here. I managed to pick another one that doesn't. And so then what we would do is again do the subtraction. Negative 3x minus 3x is 0. Negative x minus negative x is also 0x squared. But we have 0x squared, and I'm going to bring down to the next term plus 9x, because then I ask myself, well, what do I need to multiply 3x by in order to get 0x squared? Well, the answer is 0. Now, I'm going to go ahead and write it here. We typically won't write this in our answer, but then what we'd have is, of course, 0x squared plus 0x, subtraction, which gets me 9x, bring down the next term, minus 3. And so then, what do you multiply 3x by to get 9x? You would multiply that by positive 3, and you would get, actually no, we are getting a remainder. Oh, good, that's actually nice. We are going to get 9x plus 3. Then I'm going to subtract. This is where I thought we weren't, but you got to be careful with negatives. 9x minus 9x, 0. Negative 3 minus 3 is negative 6. And so the way you would write this answer is that this is equal to the division. I won't rewrite the problem out. It's equal to 2x cubed minus x squared plus 3, and then we write minus 6 over 3x plus 1, because it's not just remainder 6, it's minus 6 over what you've been dividing. Alright, so that's really all there is in this video, is this long division. We will talk about this a little bit more as far as in the next section about how to use this. One thing that I will write down here, we've kind of already talked about it, but it's an important enough concept that I'll put it down here, and it's what's called the factor theorem. And the factor theorem is a polynomial f at x has a factor of x minus k if and only if f at k equals 0. We'll actually go ahead to wrap up this video. We'll prove this. Because remember, theorems can be proven, and we don't do them that often, but you know, it is useful to do them. So a polynomial, well, that kind of is a factor, if and only if. So because it's an if and only if, we have two directions to prove. So we're going to go what I call the forward direction. So we're going to first start with f at x has a factor, or not is, has a factor of x minus k. Now, just from our division there, we know that if it's a factor from our division algorithm, if f at x is a factor, has a factor of x minus k, then the remainder, r at x, is 0. So let's write my division algorithm down. F at x is equal to d at x times q at x plus r at x. Now, what am I dividing by? Well, because it's a factor, I'd be dividing by x minus k. So f at x is equal to x minus k times my quotient, which I don't know, I don't care, plus, well, r at x is 0. So that means I can write f at x is equal to x minus k times q at x. Well then, let's evaluate f at k, because that's what we're trying to show, is that f at k would be 0. Well, f at k being 0, this means that I have k minus k times q at k. Now, I don't care what q at k is, because this is going to be 0 times q at k, which is just simply 0. So f at k equals 0. Now, what I want to show you here on this proof here is we started with the forward direction. So what I mean by the forward direction, because this is if and only if, so it has to go both ways, is that, well, what is forward direction? So f at x has a factor of x minus k. So we start by assuming that is true. F at x has a factor of x minus k. Then, well, what do we know? Because it's a factor, from the division algorithm, that means my remainder is 0. So I write my division algorithm down. F at x is equal to d at x times q at x plus r at x. Then, well, what I'm dividing by is the x minus k, and then I have this q at x, which I don't know, I don't care, but then the remainder is 0. And then all we did is substitute k in, and we came to the conclusion that f at k was equal to 0. So we just didn't say, well, it's 0. We came to the conclusion by doing some logical arguments here. Now, technically, that's not a full proof. You should go the other direction, starting with f at k being 0, and then proving that x minus k is a factor of f at x. But we're not going to go. We're not going to do that proof. It's actually fairly similar to what we did this direction, but we just did one. Now, in the next video here, we're going to be talking about polynomials and zeros more. So some of this long division might come into play again, but we'll also talk about how we can find zeros of these functions, of general polynomial functions.